Hey Math 1 students, this is Mr. Dobner, and today we are looking at the 1.5 Ready, Set, Go skill notes. So let's jump on in. You can see in this box here, gang ready, we're going to visualize our thinking. In math, it is very important to represent patterns in different ways. You've been doing that already, all throughout so many of these tasks. And primarily, we're going to be representing these patterns through tables and graphs, something that we're going to even do right here. Indicate on the table where you see the rate of change of the sequence. Well, my goodness, as you're looking at the inputs and the outputs, we've got our inputs. These are our X's. We've got our outputs right here for our Y's. You can look at the Y values and see we're going from 3 to 5 to 7 to 9 to 11. We're getting larger. So in mathematics, we will get larger using operations of addition or perhaps multiplication. When you look at going from 3 to 5, you might notice, I hope you'll quickly agree, that you're adding 2. And more to the point, this pattern continues. That's the most important thing. That didn't just happen once, but you can see that going from 5 to 7, you're adding 2. From 7 to 9, you're adding 2. From 9 to 11, you're adding 2. This leads us to see that we have an arithmetic sequence. And for this arithmetic sequence, we can say that the number that we're adding consistently is called our common difference. So, that is something that we have been working on quite a bit with. Our common difference is going to equal a 2 because we are adding the preceding term by that value of 2 each time. To get to our next term, we have an arithmetic sequence. Look, we can graph this just as we had 1, 3. That's 1 to the right, up 3. They've given you each of those 5 points plotted out. Now, by the way, we always want to label our axes. We should have an X and a Y there. But guys, look at this. As you're just looking at this, I hope you can see that this first point, how do we get to the second? We're going up. And by how much? Well, you can see that we are adding a 2. Look, as we're coming this way, we're going up again. What's happening? We're adding a 2. And this is going to be consistent just as well. This is how you can see that common difference, even in a graph. So, whether it's with a table or with a graph, you can determine that you have an arithmetic sequence. You can even see that common difference. Let's take a look at this next problem right here. It says, below you're given various types of information. Write the recursive and the explicit functions for each geometric sequence. While for a geometric sequence, I hope you remember, as we've been talking, in class, that really what you're going to see is you're not adding a constant to go from term to term. Rather, you are multiplying. And I think as you're looking at this 3 to 6, well, we're going to multiply by 2. Going from 6 to 12, once again, you're multiplying by a 2. Likewise, from 12 to 24, and so on. Each and every time, 2 times the previous term would get you your current term. We're going to try to find recursive and explicit functions. We're going to also assume the first term is term 1, not term 0. So we could go ahead and make ourselves a little table. And tell you what, I'm going to move this table even a little bit more over to the side here. I'm going to say n is my number of my term, my input, And then we could have f of n, which would be our output. And we'll say our first term was a 3. Our second term is a 6. Our third term is a 12. Our fourth term is going to be 24. You get the idea. Our fifth term is going to be 48. And just like before, even right here, you can see in this table, in this different representation right here, you can see going from term to term to term, we're multiplying by 2. Now again, when you have a geometric sequence, we can say that that constant multiplication is called the common ratio. The common ratio here is a 2. So we'd actually like to find our recursive function. Now, our recursive function, you might have recalled, was always relating how you can find your current term by looking back on your previous term. And what we're seeing is, just like Mr. Rabin said in the previous video, if you had an n right here, and if this was your f of n, which would be your output, to know what you're going to find, you'd have to take your previous term and multiply it by 2. So what would be your previous term? Well, the previous term number would be n minus 1. So this would be f of n minus 1 right here. So what we're going to see is, just like we've been seeing with this arithmetic, f of n is going to be the previous term, which is f of n minus 1 multiplied to 2. So I hope you remember in class, we've been talking about this quite a bit. We've been mentioning that this is never enough for a recursive formula. For the recursive formula, you definitely want to refer to the now and the previous and indicate what that change is, whether it's through multiplication or through addition. Here it's geometric, but we also have to name where we are starting. And guys, you can see pretty quickly we're not starting at the 0th term. We're starting at our first term. So we'll say f of 1 equals 3. So it's very easy to forget about naming what you begin with. And in this case, just like we had on our previous lesson, we're beginning with term 1. All right, well, at this point, we just have to move over to the explicit function, or the explicit formula, we should say. Well, how do we get to that? Well, very similar to what we've been doing in class. Let's just take a look at the 3 here. We can recopy that as a 3. When we're writing this 6, however, rather than writing it as a 6, we can write that as 3 times 2. When we are writing this 12 here, we're just going to put in one more multiplication of 2. Right here at that fourth term of 24, we'd have 3 times 2 times 2 times 2. And you get the idea, I hope. What we're going to see, even in this next one right here, I hope you can quickly see that there is repeated multiplications of 2. What we can do is write that as an exponent. 2 times 2 times 2 times 2. There are 4 2's, so this would be 3 times 2 to the 4th. Right up above here, this is 3 times 2 to the 3rd. This, with 2 2's, 3 times 2 to the 2nd. This would be 3 times 2 to the 1st. And actually, right now, you could say, well, here there are no 2's. You could even say that there are 0 2's multiplied together. And by the way, you can quickly check on your calculator, too, what 2 to the 0 is. But all the same. But to help us really visualize what we have here, please pay attention to the term number that we have right here and these exponents. And that's really what we'd like to look at. You can see with term 1, we would have 0 2's multiplied, or we'd have a power of 0. With term number 2, we'd have a 1. With term 3, we'd have a 2. So in other words, what we're seeing is the exponent is 1 less than the term number. And how could we write that in math, with mathematics? We could say that that power would have to be 1 less, subtract a 1 from the term that we're working with. So this is going to be our exponent. So what we're really seeing is this. When we're at this nth term here, we should see a 3. All of these patterns have a 3. We're going to have a multiplication of 2, but we're going to have 1 less than that term number. So we're going to have n minus 1. So that's really what we've got for our explicit function, or our explicit formula. Our f of n is going to have 3 times 2 to this n minus 1. So that's the pattern that we've noticed. We're last going to be asked to graph and to clearly label our axes. So tell you what, as we're looking right here, we definitely want to label our axes with an n and an f of n. For our n being our term number, it looked like we went 1, 2, 3, 4, 5. So we'll try to get these equally spaced here, or as close to it. We don't have grid lines for you. But look at the outputs. Look at these f of n's here. And, you know, as we're just paying attention to these numbers right here, we're going to notice that we are seeing multiples of 6. We very well might use that to our advantage as we're trying to make a scale. So perhaps that could be helpful. That's not the only way we could scale it. But let's see what would happen if we had a 3 obviously is not a multiple of 6, but it's halfway between. So if we had a 6, this would be a 12. We'd have 18. 6 times 4 is 24. 6 times 5 would be a 30. 6 times 6 is 36. You get the idea. 42. Then we go up to 48. So the reason why I'm doing this is it might be friendlier numbers. We'll have 1, 3, so we'll go just halfway up here. 2, 6 would be a little bit higher. 3, 12 would be about right here. 4, 24 would be right here. And finally, 5, 48 would be just like so. So, again, you know, without grid lines, this is a pretty good estimate as to what we're doing. And hope this is making sense. Good luck to you guys.